So today we're going to talk about radiation, okay? So if you guys know, there's different radiation emitters. I'm not sure if it's ERS or ORS, but do you guys know the different radiation emitters? There's alpha, and there is beta, and there is gamma. Okay. You don't really need to worry about alpha emitters because we should really have no access to alpha emitters. Okay. Beta emitters is like where you have like a high energy compound and an electron gets kicked off another compound. So we're usually kicking off an electron with a beta emitter. And beta emitters are probably what you've seen, like tritium, H3, C14, you've heard of C14, and what we use in our lab is P32. The important thing about beta emitters is that we can shield, we can protect ourselves from this radiation, okay, with shielding. So we'll go over that. Gamma emitters are electromagnetic wave that can go through most things. It's hard to shield. I think I'm going to redo this. So I-125 is a gamma emitter that sometimes gets used in 306. Okay. So like we said, P32 is a beta emitter. It has higher energy, but like I said, it's easier to shield. And usually what we use to shield it is 1 centimeter of plexiglass. So there's a couple of things you should know. Let's see. Beta emitters. But, okay, so this is a beta emitter, right? P32 is a beta emitter, but it has a low penetrating power, so like I said, it can be shielded. And the way so let's talk about a little bit about measuring radioactivity, okay? So radioactivity is measured in curies. Curies. So a lot of times when you go to buy a bottle like P32 or something, it's going to be how many millicuries is in that bottle, okay? Now, so it's like when you're buying the bottle. And then you have a radiation, like how much a radiation dose. Okay. Radiation dose. How much were you exposed to is going to be units of rads. RADS. But those units of rads don't take into account what kind of radiation it is, right? If it's an alpha, beta, or gamma. Because you can imagine Like you don't want a strong gamma emitter because that can penetrate all your skin or something, you know. So it's going to depend what kind of emitter it is. So in order to take into account how it's going to affect your biological system, okay, those get measured in REMS. So we correct this value of rads, okay, for the kind of radiation it is, and so that's expressed in REMS. So to take into account it's expressed in REMS. Okay, so this gets confusing. You'll see stuff for radiation in Curies, RADs, and REMS. Okay, so like Curies is when you're buying it from a company. RADs is like how much exposure you're being like exposed to that radiation, but again, that doesn't take into account the biological effect it's going to have because of the type of radiation it is. So that's more relevant is REMS, REMs. Okay. So there are some limits set by like OSHA, so for our safety working for conditions. So the max whole body dose is 5,000 millirem per year. Okay. If you're a student, it's 3,000 millirem per year. Okay. And you guys can look this up. Like I think like air flight attendants, they get exposed to a lot of radiation, like way more than you'll hopefully ever be exposed to in a research environment. Okay. So if you're at all worried. You can use a pancake meter to detect gamma radiation. So they're called pancake meters or a Geiger counter. And one showed up in our lab. I don't know where it came from. But if you guys want to go see what that looks like. So it's a Geiger counter. Also called a pancake meter. Did I spell pancake wrong? And you'll see on the Geiger counter it has like counts per minute. So it's just like you'll hear beep, 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 if you have a lot of radiation. And so about 3,200 counts per minute CPM on a pancake meter is about equal to 1 millirem per hour of gamma rays. Okay. Okay, I should really look this up, but the inverse square law of radiation. So there's this the inverse square law. Have you guys heard of the inverse square law? Somewhere else maybe. But basically, it's like radiation decreases as the square of distance from the source. Okay, so it just means that like if I move 1 foot away from my source, I decrease my exposure by half. If I move 2 feet away, I've decreased my exposure like 4-fold. So it's not like by 2 you square it. If I go 3 feet back, I've decreased my exposure by 9-fold. Okay, so the main point to drive here is that if you keep your distance, you're really reducing your exposure, which is a good thing. Okay, so there's this inverse square law. So we have this thing called ALARA principles, and to me this is the most important part of this whole radiation training. Okay, is ALARA. As low as reasonable, achievable. Okay, as principles. Okay, so there's 3 principles. 1, you want to minimize your time. Okay. That means you want to minimize the time that you are exposing yourself to any radiation. How do we do that? That means we're very well prepared. We know exactly what we're going to do when we're going to lab. We've done a dry run without taking out that P32, without taking out that radiation. We've gone through and said, I'm going to pipette this into here. I'm not taking out my radiation, putting it on the bench and saying, now where did I put that pipette? How much I got to put in? No, 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 no. We're very well prepared when we go in to do a radiation experiment. We know exactly what we're going to do, where it's going to go, and where it's going to go afterwards. We have it all planned. And the reason we're doing this is because we want to minimize the time that we have to expose ourselves to this radiation. Okay? 2, we're going to maximize our distance, right? Because of that inverse square law, right? So when we're doing that radiation, we're not here with our reproductive organs as close as possible to the bench, exposing it, right? We're kind of step back. We got our arms. We don't want to do it so we're clumsy, but we want to keep our distance as much as we can. Okay? We don't want to be looking at it up close. Maximize your distance. And then 3 is we want to use shielding. Right? We're working with these beta emitters. They're easily shielded. Plexiglass is clear, so we have these trays that we just put in front of us and we work behind it, and it's really easy to block that radiation. Okay? So we always want to make sure we're using shielding. We have waste cans that we dispose stuff in, made out of plexiglass. That's where we put it. Okay? Okay, so let's see. What else I want to tell you guys? And just a little bit of point of reference from solar radiation and from potassium in your body, you're exposed to 300 to 400 millirems yearly anyways. Okay, and smoking and flying increase your exposure to radiation. Okay, it's really important that you know there's no eating, no food or drink in any of the labs, but especially in 306. Okay, it really shouldn't be, because that's number one way people get really harmed from radiation, is that they ingest something that's radioactive. Then it's really hard to how do we get it out, and then you're exposing all your internal organs to that. So that's really the danger. Okay, really only necessary material should be brought into that radioisotope room 306. Okay, so if you can leave it somewhere else, it's probably a better idea, just to really reduce any risk of contamination. Like we said, solid waste generated in any of our experiments is wrapped in plastic and disposed of in the special container. Okay? And if an accident occurs, stay calm. Don't spread the spill. Okay? You can contact me or Daniel Crocker, who's a radiation safety officer. I think he had to sign off on your key request. Hopefully you guys have met him. Wash your hands, okay? Gently. You don't want to break the skin, okay? But I think that's it. Like I said, this is the most important thing to me, is these are LARA principles, is minimize your time, maximize your distance, and use shielding. Okay? And no food and drink in the lab.